In this lecture, we're going to talk about nutrients and nutrient cycling. We've just talked a little bit about kind of an introduction to biology and ecosystems. We moved from there into a little population dynamics and then into discussion of dissolved oxygen. We prefaced that by talking a little bit about the different kinds of bacteria. We said they play several important roles in environmental engineering. And one of those roles is that they serve as mediators of nutrient cycles. And nutrient cycles are what allow life to occur on Earth. And so we're going to be talking today about a few of the main nutrient cycles, what we call biogeochemical cycles. The five most basic are carbon, oxygen, nitrogen, phosphorus, and sulfur, although there's lots of other cycles, chromium cycles in the groundwater, other metals also go through cycling. We're going to specifically dive into carbon, nitrogen, and phosphorus as the main three that we're going to hit. We're not going to hit oxygen and sulfur quite as much, although you already know something about oxygen dynamics from our discussion of dissolved oxygen. So you'll hear this term nutrients, and this can either refer to carbon, nitrogen, and phosphorus, or just nitrogen and phosphorus, depending on the context. We'll use it in both contexts in this class. For this lecture, we're going to talk about it in terms of carbon, nitrogen, and phosphorus, but you'll also hear about it most likely just referring to N and P. So the first step is carbon cycle, which we've already talked about to some degree. And there's mainly two natural mechanisms for carbon cycling, and those are photosynthesis and respiration. So photosynthesis says I'm going to take some energy from the sun, add carbon dioxide from the air, and some water, and we're going to get out this CH2O plus oxygen. And CH2O is just something we use to represent complex organics, complex carbon-containing compounds like the actual plant leaves, for example, would be in the CH2O right here. And then respiration is the opposite of photosynthesis. It takes H2O, we add in oxygen, and we get out carbon dioxide, water, and energy. So photosynthesis is something mostly plants do, as well as some photosynthetic bacteria, whereas respiration is something animals do, as well as other kind of chemoautotrophs. Some bacteria do it as well. And essentially, the main carbon cycling on Earth is going back and forth between photosynthesis and respiration. We also have talked about carbon in the context of the carbonate system, which is what's going on with carbon in the aquatic environment, and we've talked about how that relates to what's going on in the atmosphere via Henry's constant, where we have CO2 aqueous divided by CO2 gas, and we said that that's equal to 10 to the minus 1.5. And thus, as more carbon dioxide gets released to the atmosphere, more is going to then partition into the aqueous phase and get introduced into the carbonate system, in which it can also transfer through different acid-base reactions to carbonic acid, and then bicarbonate, carbonate, and also into calcium carbonate. Volcanic activity is a big source of carbon and carbon dioxide to the atmosphere. So you can see in this figure down here, you've got volcanic activity up here. We've got carbonate rocks, calcium carbonate, CaCO3 solid, thermal vents in deep oceans. All of these can contribute carbon dioxide. We have the plants over here. You can see respiration and photosynthesis going on here, where photosynthesis is taking up the carbon dioxide, and then you could have plants and well, not really plants, but animals respiring carbon dioxide back. The chemoautotrophs here, respiration to create carbon dioxide. So this is kind of the complex food web here of essentially consumers and producers that are all respiring carbon dioxide into the aquatic environment or the atmosphere. And so the main two things, again, that we want to just focus on is photosynthesis and respiration, cycling those. Now, what is the biggest kind of interference in the carbon cycle that we have? Well, these days it's carbon dioxide emissions from fossil fuel combustion. We know carbon dioxide is a greenhouse gas. As we put more and more into the atmosphere, that has lots of effects, as we've talked about previously, but also more is going to go into the aquatic environment. And then, as we've also talked about, that will eventually wind up lowering the pH of aquatic systems as more carbonic acid is introduced. And that's the ocean acidification problem that we know about. So that's the carbon cycle in a nutshell. Now we're going to move on to the nitrogen cycle. Next page. And here again, we have bacteria that are going to be mediating a lot of these reactions. We've talked about some of these terms before. I want to, though, just kind of on the right side here, draw a little diagram with some of the main components of the nitrogen cycle. We know that there's nitrogen gas up in the atmosphere. So that corresponds to in the figure over here, up here. And we're going to have a process by which that nitrogen gas gets put into ammonia, NH4+, or the ammonium ion. That process is what we call fixation, nitrogen fixation. So up here on the top, the nitrogen cycle, you can say, starts with nitrogen fixation. This is a process where N2 gas goes to NH4+, and then NH4+ undergoes an acid-base reaction to create ammonia. And this process, nitrogen fixation, you may know that there are certain crops that can do this. There are plants, bacteria that can do this as well. Legumes, which include clover, beans, alfalfa, peas. These are all capable of taking nitrogen from the atmosphere and putting it into the roots of the plant. And because plants need nitrogen in order to grow, this is great because it kind of self-fertilizes the crop, but also then those crops wind up having protein in them from having nitrogen available. And if you could compost those plants, or you could use them as fertilizer for other plants as well. So fixation takes nitrogen from the atmosphere, puts it into ammonia, and then we've got the next step where we're going to convert that ammonia into NO3-, which is nitrate. So this is nitrogen gas up here. This is the ammonium ion, and then NO3- is nitrate. This process is what we call nitrification. We mentioned nitrification already before when we were talking about dissolved oxygen, because we said ammonia exerts a biochemical oxygen demand, the NBOD, in that it takes some amount of oxygen to degrade ammonia. And so the reaction I'm going to write up here on the top for nitrification is we take some NH4+. It also takes some bicarbonate for this to happen, 2HCO3-, and then we've got our oxygen, and that typically one-way reaction, not reversible, is going to go to NO3-, which is the nitrate, plus some carbon dioxide comes out, some water, and some energy. So again, this conversion of the nitrogen in the form of ammonium to nitrate is called nitrification. We can also convert that that nitrate back into nitrogen gas via first converting to nitrite on the way, and this process is called denitrification. So denitrification, the reaction is, the overall is we've got NO3 minus going to NO2 minus and then to N2 gas. And this is again all mediated by bacteria. And now we've closed the loop. In the meantime, NH4 as ammonium is available to plants and animals. This is the sort of fertilizer form that plants can use. And when we eat plants and animals, we also get nitrogen in our bodies from that. So the ammonia can go through a process called biosynthesis, in which it's converted to what we call organic nitrogen. So this is where plants and us will take ammonia, the amine part of the ammonia, make amino acids, and then make proteins, which are organic nitrogen. And then when we die, or when we create waste, or when plants and animals die, that organic nitrogen can be converted back into ammonia via a process called ammonification. So again, biosynthesis up here would be NH4 plus goes to organic nitrogen. Ammonification would be organic nitrogen goes to NH4 plus. One thing I didn't write was sort of the overall reaction for denitrification, just FYI, would be it takes C10H19O3N plus 10NO3 minus goes to 5N2, so there's nitrogen gas, plus 10CO2 plus 3H2O plus a little bit of ammonia plus 10OH minus. Not critical you understand this, but it's a combination of a couple of reactions. You don't see the nitrite popping up in there. It's an intermediary between the overall reaction that's happening. So again, these are all natural processes. What is our main impact on these processes? Well, for one, the main thing, which we'll talk about in a little bit, is when we add too much nitrogen to the natural cycle, we can disrupt what's happening in especially aquatic environments. And how do we do that? Well, we do that mainly, it starts with a process which we call industrial fixation. Industrial fixation is mainly accomplished by something called the Haber process. Haber process is an industrial method, a way that we can use energy, electricity usually, in order to pull nitrogen out of the atmosphere and actually make ammonia out of that atmospheric nitrogen. And that is the way we make what we call synthetic fertilizers. So most of the cheaper fertilizers that you would apply to your lawn or your trees or your plants, Miracle-Gro, that sort of thing, comes from this process. When we apply those fertilizers, if they don't all get into the plants themselves that we're growing, if we apply them in excess and then they have a chance to run off, more nitrogen is going to enter the aquatic environment than would otherwise. And so while this process can cause some serious problems in the environment, it's also been instrumental in feeding the world's population, in that this is a way in which we can get protein into our diets. And so it's an incredibly efficient process that's really transformed society and allowed a lot less people to be farmers than used to be. But it also can have some serious consequences if we don't manage the fertilization of the crops and the nitrogen cycle well. Okay, so that covers nitrogen cycle. Now we're going to move to the phosphorus cycle. Next page. So phosphorus cycle, we've got a little image down here. I'm going to draw my own image above it that I think might be a little easier to follow, but is basically the same idea. And so I'm going to break the phosphorus cycle into essentially the 4 parts. We've got dissolved parts and particulate parts, and then we've got organic parts and inorganic parts. So we start up here with particulate organic phosphorus. Particulate organic phosphorus could be like us, right? We're not dissolved and we have phosphorus in us. Any kind of organism, or even like a sediment particle that has some organic phosphorus on it, could be this. But we could think of it as like algae or little plants and animals, that kind of thing. When those decay, some of that particulate organic phosphorus can dissolve into water and become dissolved organic phosphorus. And the way that it becomes particulate organic phosphorus is typically that the dissolved organic phosphorus is taken up by let's say it's some algae or something. It's going to absorb and take up that dissolved organic phosphorus from the water and put it into its body burden, into the particulate nature. Also, when these things decay, they can form dissolved inorganic phosphorus. And inorganic phosphorus is typically in the form of orthophosphate, this PO4 molecule. And this can then be taken up by plants and, form particulate organic phosphorus. Can also be, those plants can be taken up by animals and via their waste or via, again, decay. That can go to dissolved organic. The dissolved organic phosphorus, again, this is organic molecules, so complex carbon-containing molecules. Those can actually decay and degrade, degrade into inorganic P. And then last we have particulate inorganic. And this is not carbon containing but particulate, and so this is typically like rocks, fertilizers, minerals that contain phosphorus. And we can either via industrial processes or directly form dissolved inorganic phosphorus via those. And so those can go into fertilizers, for example, which we would apply to plants. Okay, so this is essentially what's happening in the phosphorus cycle all the time. Interconversion between dissolved, particulate, organic, inorganic. And unlike with nitrogen and carbon, most of the phosphorus gets bound up in the particulate form, in sediment, for example. And so that's where we tend to find it in the aquatic environment. Now, that's just a broad overview of the phosphorus cycle. I'm not going to show any of the reactions. The phosphorus cycle is more complex than the nitrogen cycle. Again, ways in which humans interfere with this is when we discharge too much phosphorus, either from fertilizer and runoff, or for a long time, detergents that we would use in our washing machines contained phosphates. And these pass through wastewater treatment plants and wound up being discharged in the environment. And this is causing problems, as we'll talk about in the next video. What are the consequences of too much nutrients? What do we actually see in the environment? And then what do we do about that? How do we treat that? We'll talk about that in the next video.